Let us now continue with the third example problem. So, here we will actually be looking at a batch reactor. Until now we have been looking at open systems. So, we have always been calculating change in enthalpy, specific enthalpy, building enthalpy tables and so on. However, here we will actually be looking at a closed system. So, we will be looking at internal energy changes, and we will look at how to calculate these internal energy changes, how to build enthalpy, internal energy tables and so on. So, let us look at the problem statement. The problem statement reads, a gas mixture containing 85% methane and the balance oxygen is to be charged into an evacuated well insulated 10 liter batch reaction vessel at 25 degrees Celsius and 200 kilopascals. The reaction vessel is designed to withstand a maximum pressure of 1068.25 kilopascals. An electric coil supplies heat to the reaction vessel at a rate of 1000 watts, and it will be turned on for 85 seconds and then turned off. Inside the reactor, oxygen is consumed completely and formaldehyde is to be produced by the reaction, where methane reacts with oxygen to form formaldehyde and water. The reaction products are cooled and discharged from the reactor. Assuming no side reactions occur, methane gas, oxygen gas and formaldehyde gas and water vapor at 25 degrees Celsius as the reference state, calculate the final temperature and pressure. Will the reactor be able to withstand this final pressure? While you are performing this experiment, the reaction vessel explodes. Assuming that the pressure rating of the vessel is accurate, what could be the possible reason? So, here you have two parts. The first part, you are actually asked to calculate the temperature and pressure. So, we had already looked at a problem where we had to calculate the outlet temperature. So, we are familiar with how to do this. So, we would just be using internal energy instead of enthalpy here. So, we will be looking to calculate the outlet temperature. We already have the value for Q. So, the Q is given at the rate of 100 watts for 85 seconds. So, we can actually calculate the total amount of heat which is supplied, and identifying the change in internal energy, you will be able to write the appropriate energy balance equation and solve it for getting the final temperature. So, from the final temperature we can also calculate the final pressure and compare it against the pressure rating which has been given and identify whether the reactor can actually withstand. In the second part of the problem, we have been asked to identify whether if the reaction vessel does explode, what could be the reason, and we will try to hypothesize a potential cause for something like that. So, let us look at how to solve this problem. Here is the example problem in terms of the flow sheet. You have an initial and final condition. It is a closed system which is 10 liters, 200 kilopascals and 25 degrees Celsius in the initial condition. It contains N naught moles of feed gas, and you know the composition of this feed gas. Initial condition is 0.85 moles of methane and 0.15 moles of oxygen per mole of the mixture. So, you have the final condition which would be 10 liters because it is a constant volume reaction vessel, and your pressure you do not know. The final pressure can be given as P at kilopascals, and the temperature is marked as T degrees Celsius. So, you also have N3, N4 and N5 moles of formaldehyde, water and methane which are in the final condition. Now, let us see how we can perform the calculations to identify the amount of heat that can be supplied to the system. So, first we need to identify the basis. Here we do not know the conditions, we do not know the number of moles in the initial and the final conditions, and that we need to perform using identify using material balances. So, for that we need a basis. So, what would be the basis? We cannot randomly assume a basis. We need to identify the number of moles which are present in the initial condition. We have been given the temperature and pressure. So, if we were and the volume. So, if we were to assume ideal gas behavior, we would be able to calculate the number of moles which are present in the initial condition. So, that is what we are going to do. So, the basis would actually be N naught moles in the initial condition. So, taking that into account, let us calculate N naught. So, N naught would be equal to PV by RT. So, P is the pressure, we have it as 200 kilopascals. So, we will call it 200 times 10 power 3 pascals, and your volume is 10 liters. So, it would be 10 times 10 power minus 3 meter cube divided by R in terms of SI units would be 8.314 times temperature in Kelvin would be 298 Kelvin. So, using this we can calculate N naught as 0.8072 moles in the initial condition. Okay. So, this would be 0.8072 moles. We now need to identify N3, N4 and N5 in the final condition. So, for that we would have to perform simple material balance calculations. So, now to identify the number of moles in the final condition, which is N3, N4 and N5, we need to know how much of methane is consumed. Since we know that all of oxygen is consumed, we can use the stoichiometry to identify how many moles of methane would have been consumed. So, first thing we need to identify is the number of moles of methane in the initial condition, number of moles of oxygen in the initial condition. We know that 0.8072 moles are present in the as a feed gas mixture. So, methane initial would be equal to 0.85 times 0.8072, which is 0.6861 moles. Oxygen in the initial condition would be equal to 0.15 times 0.8072, which is 0.1211 moles. So, now we need to identify how much methane is consumed. So, we know all of oxygen is consumed. So, 0.1211 moles of oxygen was consumed. According to stoichiometry, for every mole of oxygen consumed, 1 mole of methane should also be consumed. So, methane consumed would be equal to 0.1211 moles. So, this implies methane in the final condition, which is N5, would be equal to initial methane minus methane consumed, which is 0.6861 minus 0.1211, giving you a value of 0.565 moles. So, this is the number of moles which is of methane present in the final condition. So, we also need to identify the number of moles of formaldehyde and water which is present. Based on the stoichiometry, for every mole of oxygen consumed, 1 mole of formaldehyde and 1 mole of water is produced. So, you can calculate formaldehyde produced would be equal to oxygen consumed, and this would be 0.1211 moles. Similarly, water produced would also be equal to 0.1211 moles. So, now that we have the number of moles of each of the component in the final condition, we can also calculate the extent of reaction. So, the extent of reaction would be, so this extent of reaction would be required when we perform the energy balances, right. We have been told to use the heat of reaction method. So, we need to know the extent of reaction. We will calculate the extent of reaction as moles final minus moles initial divided by the stoichiometric coefficient. So, if you were to use oxygen, you would have 0 minus 0.1211 divided by minus 1, giving you 0.1211 moles. So, that is the extent of reaction. So, this can be used while we perform the energy balance calculations. Now that we have performed all the required material balances, we can start with the energy balance calculations. Here it is a closed system, unlike all the systems which we have been looking at till now. For a closed system, the equation would be Q minus W equals delta U plus delta Ek plus delta Ep. So, here there is no change in kinetic and potential energy, and there are no moving parts. So, you have work also equal to 0. So, you end up with Q equals delta U, and once you have this equation, we have to calculate delta U. So, for that we have been told to use the reference states of methane gas, oxygen gas, formaldehyde gas and water gas at 25 degrees Celsius. So, let us take the reference states as given in the problem, which is methane gas, oxygen gas, formaldehyde gas and water gas, all at 25 degrees Celsius. using this reference state, let us build the internal energy table. So, the table would look like this. You would have methane, oxygen, formaldehyde and water. You would have N initial and U cap initial, N final and U cap final. So, initial moles are 0.6861 and 0.1211, and you do not have any formaldehyde and water. In the final condition, you have 0.565 moles of methane, there is no oxygen. You have 0.1211 moles of formaldehyde and water. So, the initial condition is oxygen and methane at 25 degrees Celsius, which is the same as the reference state. So, the internal energy for these two would be 0, and for the final condition the temperature we have kept it as T. So, we will have to use some internal energy values for this. We will call this as a U1 cap, U2 cap and U3 cap. So, we need to calculate U1, U2 and U3 to identify the temperature which we can reach, and we will have to perform these calculations using CV instead of CP. So, we know that UI cap would be equal to integral 25 to T CV dt. So, we have always been using CP. So, we will use CV here. So, if it is a solid or a liquid, CP will be roughly equal to CV. However, here everything is a gas. For a gaseous system, you would have CP equals CV plus R. So, you will calculate CV as integral 25 to T Cp minus R dt. So, Cp value is readily available from your tables or and from textbooks and reference books. R would be 8.314 joules per mole Kelvin. So, you will use the R value as 8.314 joules per mole Kelvin, and you can actually substitute this value here to calculate the value for CV, and you will be able to perform calculations to get U1 cap, U2 cap and U3 cap. So, using the Cp values and the R value, we will get U1 cap as 0.02599 T plus 2.7345 times 10 power minus 5 T squared plus 0.1220 times 10 power minus 8 T cube minus 2.75 times 10 power minus 12 T power 4 minus 0.6670. This would again be in kilojoules per mole. Similarly, you can get a U2 cap. Similarly, you can get U2 cap as 0.02597 T plus 2.134 times 10 power minus 5 T squared minus 2.1735 times 10 power minus 12 T power 4 minus 0.6623 again kilojoules per mole. So, your final U cap U3 cap would be 0.02515 T plus 0.3440 times 10 power minus 5 T squared plus 0.2535 times 10 power minus 8 T cube minus 0.8983 times 10 power minus 12 T power 4 minus 0.6309 kilojoules per mole. So, again you will be able to get the Cp values from the textbook or from other reference books. So, you can substitute that to get Cv value and you will be able to calculate the internal energy changes as I have shown here. To calculate the change in internal energy delta U, we need the internal energy of the reaction as well. So, delta U would actually be equal to sigma of N final times U cap final minus sigma of N initial times U cap initial plus the xi which is extent of reaction times delta U r, which would be the internal energy of reaction. So, here we already identified the internal energy of the final and the initial conditions using the polynomials we have. We also have a delta UR, we also have the xi value, we need to calculate the internal energy of reaction. So, for calculating the internal energy of the reaction, we first need to know the standard heat of the reaction. So, the standard heat of reaction can be calculated using the heat of formation of all the compounds. So, this would be heat of formation, summation of the products where you have stoichiometric coefficient times heat of formation minus for the reactants you would have the stoichiometric coefficients times the heat of formation for the reactants. So, now taking that into account, we have formaldehyde and water as the products and we have methane and oxygen as the reactants. So, obviously oxygen would not have any heat of formation because it is an element. So, you would end up with all of them have stoichiometric coefficients of 1. So, the equation then becomes heat of formation, standard heat of formation of formaldehyde plus standard heat of formation of water minus standard heat of formation of the reactant which is methane. So, doing this we can actually calculate the heat of reaction. So, getting the values for these from the table, it would be minus 115.9 plus minus of 241.83 minus of 74.85 and you would get a value for the standard heat of reaction as delta HR as minus 282.88 kilojoules per mole. Now, we need to calculate the specific internal energy change associated with the reaction. So, which would be internal energy of the reaction delta UR dot. So, we know that we can calculate this from the heat of reaction using this correlation, heat of reaction minus RT times sigma of gaseous products the stoichiometric coefficients minus the summation of the stoichiometric coefficients of gaseous reactants. So, this is the equation. So, here we have all the components reactants and products as gaseous components. The stoichiometric coefficients for all of them are 1. So, you would end up with actually 1 plus 1 minus 1 minus 1. So, this term actually goes to 0 and you end up with a standard heat of reaction to be equal to the internal energy of the reaction. So, numerically they are the same, which would be 282.88 kilojoules per mole. So, now we have all the terms, we have the N final U cap finals, N initial, U cap initial, xi and your heat of reaction, sorry, internal energy of reaction. Now that we have all these values, we can plug it into the equation for the heat balance, which is Q. So, in the problem statement we have been told that heat is supplied by an electric coil at a rate of 100 watts for 85 seconds and then it is stopped. So, the amount of heat which is supplied would be Q equals 100 joules per second times 85 seconds. So, this would give us in terms of joules, which is 8500 joules or 8.5 kilojoules. So, the total amount of heat supplied would be 8.5 kilojoules. So, we have all the terms. So, we have a polynomial representing the change in internal energies. So, substituting all that into the general energy balance equation, we would end up with a polynomial which would be minus 1.926 times 10 power minus 12 T power 4 plus 0.09963 times 10 power minus 8 T cube plus 1.845 times 10 power minus 5 T squared plus 0.02088 times T minus 43.29 kilojoules per mole as the equation equal to 0. So, Q has also been accounted for in this equation and by solving this polynomial we will be able to get a temperature of 1091 degrees Celsius and this reaches a pressure of P equals nRT divided by V. So, this would basically be the number of moles of in the final condition. So, which would add up to 0.8072, and so you have 0.8072 moles in the final condition. R is 8.314 and you have temperature as 1364 Kelvin. So, we have 1091 degrees Celsius, which is equal to 1364 Kelvin. So, this divided by volume, which is 10 liters, which is 10 times 10 power minus 3 meter cube. So, you are left with a pressure of 915 kilopascals. So, this is below the threshold given for the problem. So, the pressure vessel should be able to handle this pressure. However, in the second part of the problem, we have been told that vessel explodes even though exactly that amount of heat is actually supplied. So, this is a problem. So, we need to identify why that is the case. So, that is because you could actually have side reactions. The side reaction which you would observe would be for combustion reaction. So, methane, when it is reacting with oxygen, can actually have a combustion reaction, and obviously the heat of reaction for a combustion reaction would be significantly higher than the formaldehyde formation reaction which we are looking at here. So, because of that you would have had a much higher temperature, which would have resulted in a very high pressure resulting in an explosion. So, that is what the problem alludes to. So, with this we have actually completed the example problem, and in the next few lectures we will have a review of all the aspects covering the energy balance concepts that we have learnt over the past few weeks. Thank you.